Comparing electric and gravitational fields. There are many similarities between electric and gravitational fields, and there is one significant difference which we'll look at the end. Firstly, electric field lines show the force on a positive charge, whereas the gravitational field lines show the force on a mass. Comparing them in more detail, I'll draw up this table. Firstly, the field due to a point mass is given by this expression, where this is the gravitational field strength, this is the gravitational constant, the mass in kilograms, and our distance from the mass in meters. The field due to a point charge, the electric field strength E, is given by the charge Q in coulombs over 4 times pi times the permittivity of free space times our distance from the charge squared. So you'll see both these expressions have basically the same format. They both obey an inverse square law. Next, the force between two masses, which is given by Newton's universal law of gravitation. The force F in newtons is given by the gravitational constant multiplied by the product of the two masses in kilograms divided by the separation of their centre of mass squared. The force between two charges is given by Coulomb's law. The force again in newtons is given now by the product of the two charges in coulombs over 4 pi times epsilon naught times the separation of the charges in meters squared. So again, the two expressions follow basically the same format, just with a different constant of proportionality. Here the gravitational constant, and here 1 over 4 pi epsilon naught. Next, the field strength. Well, for gravitational fields, that's the force per unit mass, so the field strength G is given by the force over the mass. The field strength for an electric field is the force per unit positive charge, so the electric field strength E is given by the force over the charge. The units of gravitational field strength are the newtons per kilogram, or equivalent units are meters per second squared. The units of electric field strength are newtons per coulomb, or equivalent units are volts per meter. The uniform fields, well, for a uniform gravitational field, there will be parallel, equally spaced field lines, and the gravitational field strength is the same everywhere. In a uniform electric field, there'll again be parallel, equally spaced field lines, and the electric field strength will be the same everywhere. Now to look at potential. Well, gravitational potential is the gravitational potential energy per unit mass at a particular point. And for a point mass m, the gravitational potential V is given by minus the gravitational constant times the mass m in kilograms over our distance from the centre of mass r. Electric potential is the electrical potential energy per unit positive charge at a particular point. And for a point charge, the electrical potential V is equal to the charge Q in coulombs over 4 pi epsilon naught times our distance from the charge r. Next, the units of potential. Well, the units of gravitational potential are the joules per kilogram, and for electric potential the units are volts, which are joules per coulomb. Now the potential energy between 2 point masses is given by minus G times the product of the two masses divided by the separation of their centre of mass. The potential energy between 2 point charges is given by the product of the charges in coulombs over 4 pi epsilon naught times the separation of those charges r. The main difference is that the gravitational force is always attractive. There's no such thing as negative mass, whereas the electric force can be attractive if we have opposite charges, or repulsive if we have like charges.